Oh, echo. I'm trying to get it on Teams instead of the web.
There we go.
But I seem to be on both or something.
Okay. Okay, folks, we've got the recording going. Welcome to the Sebastian. Welcome to the October Northwest C++ users group meeting. Tonight we've got Peter Williamson talking about Remedial C++ 17. So I don't think we've got any announcements at the moment. CPPCon was last month, so pick that up again next year. Still looking for a couple of speakers for next year, so if anybody wants to speak, just let me know. And with that, we'll turn it over to Peter. Thanks.
Howdy, everybody. Let's get started. Just a second while I bring up the slides. There we go. So tonight we're going to talk about Remedial C++ 17. So why are we talking about Remedial C++ 17? Why are we only now talking about C++ 17? Isn't it like 2022, 5 years after the language spec was approved? Yep, that's exactly right. And because it's been about 5 years, all the compilers support it now, including those weird ARM compilers that only run on your phones and things like that. So now it's getting to the place where the average person is able to use it and make use of the features. So now that it's actually here in a way that we can use, I thought, let's take some time and learn a little bit more about it. So if you have questions, go ahead and use the raise hand feature, this one here. I'm going to lower my hand. So if you see a bar, there's something that looks like a hand in the middle of it. Just use that. And I'll try and leave about 15 to 20 seconds after every slide of silence. And if you have a question, then go ahead, and I haven't acknowledged your hand being raised, then just go ahead and work the question out when there's some silence. So it's much better for you, I think, to not have to hold your questions to the end, but be able to ask them when you have them. So how this came about originally is on the Chrome team. It was always about 5 years after a new language version became available that we were able to use it. So I started making presentations back for C++ 11 when it got to be about 5 years later, then for C++ 14 when it got to be about 5 years later. Now it's time for C++ 17, and you guessed it, 3 years from now, I'll be ready to talk about C++ 20. So with that said, let's get moving. So the C++ landscape. Originally, there was just C++, and then it was codified as a standard as C++ 98. And all throughout the OXs, they worked on trying to make a new standard, which they were calling C++ OX, in hopes it would come out in a year like 2007, 2008, or maybe even 2009. It finally came out in 2011. The fact that it took them so long made them think, you know, we should develop a 3-year cadence and just take whatever's ready at every 3 years and ship that. And that's what they've been doing ever since. And I have to say it's worked spectacularly well. I think that was a really good choice on the committee's part. So the book I'm going to be talking mostly about is this one here, C++ 17, The Complete Guide by Nikolai Josuttis. There's a website listed there, and it's also the links at the end. Lloyd will send around these slides later to everybody in the Northwest C++ user group, so you can get the slides and click on the link if you're interested. The book comes in either a physical version like I have, or a PDF version. And the cool thing about them is as he's writing the PDF version, he'll produce new versions from time to time. Now, C++ 17 is already baked, but for any overachievers out there of you who want to read about C++ 20, he's still writing that book. And as he adds additional installments, if you get the PDF version, you'll get an email that says, hey, there's a new installment. You can go down now the new installment. Of course, once you get a printed version, you're sort of stuck with the printed version. So this book was the source for many of the examples of this talk, and I also decided to organize this talk following the list of chapters in that book. Now, tonight I'm going to give you an overview. There really isn't enough time to go into depth of the, 418 or so pages of this book. So we're going to cover everything at a higher level. And if you want to get it in more level, you can go into this book, or also there's several other links at the end that'll be a great place to learn more about it. So what changed in C++ 17? At first, when I was practicing the talk, I thought I would read out all of these, but then we're going to talk about all of them later, so we'll go through them one at a time. So this is the first part of language changes for C++ 17. And this slide is part 2 of language changes for C++ 17. But language changes is only half of the new changes we get in C++ 17. They change both the language and the standard library. And this is a quick list of the library changes. Now I checked my list of slides, and just talking about the language, I have 92 slides. So we're not going to get to the library changes tonight, but hang on, because in April, I'm scheduled to give another talk where we'll go over the library changes. So let's jump right into the language changes. First, we'll talk about structured bindings. So there's always some relationship between the photo and whatever it is we're talking about. In this case, relationship is bindings. Knowing that should give you a clue about what to do with the other photos. So what is a structured binding? What does it do? It gives local names to structure members. So for example, this is another example I got from Josuttis' book. Let's say you have a structure that has an int and a string member. So you'll just declare a structure, and then you'll do an assignment to it. And the purple part is the new part. So all of my slides, the purple part will be something new that's been added to the language. So what this statement actually does is it'll create 2 new variables, u and v. U will get the integer, and it'll be of type int. V will get the string, and it'll be of type standard string. So this is sort of like a way of getting multiple return values out of a assignment. So when would you use it? You'd use it if you want to give local names to variables when a function returns a struct-like item with with a struct-like item with multiple values in it. Another cool thing is that if a function returns a struct, then doing this assignment will keep the struct alive and in scope until you exit the scope. And that's structured bindings. Initialization inside if and switch. I'm sorry, I promised to pause for a few seconds at the end of every slide. So I'm going to pause now in case there's any questions. All right, let's keep moving. So initialization inside if and switch. So what is it? It lets you initialize something right before you're about to check it. So once again, look at the purple part of the slide. The example is if return code equals file open of foo, then you can do the assignment and then check for success right inside of the if statement. And you can do the same thing with switch statements. Now, when would you use it? So I'm not sure that I actually recommend using this. Generally, I think the code is clearer with the init outside. I like to write boring code. I think the more boring code is, the more maintainable it is. And most of the code we write is going to be maintained for many years. Now, maybe if you're a game programmer, don't worry about maintenance. All you have to do is a few patches and you're done most of the time. But if you're somebody writing something like me, like a large browser or word processing programs, then you want to think about maintenance, and maybe it's not quite as readable. Inline variables. Oh, that's right. I'm going to pause for questions.
Sorry, is the what is the scope of the RC? Is it just within the body of the if?
It's just within the body of the if.
Okay.
So it should be gone by the time the if statement is over.
I've heard that as an argument for why people should use like initialization in the if statement, because the scope is bound just to the if statement.
That's a good reason. That might be worth doing.
Yeah.
Generally, I worry less about keeping scopes as minimal as possible, but that's just a personal style choice on my part. I could understand that others have a more restrictive style than I do. Anything else?
Can I ask about the previous slide?
Sure thing.
Well, the previous item. Okay. When you said it keeps the struct alive, but I thought the idea was you had 2 variables, ID and val, which were members of the struct, but the struct itself, where did it go?
Right. So imagine there's a temporary variable unseen to you that is being held alive. So the struct is being returned by the function getStruct. It goes into a temporary variable of automatic scope or on the stack, which is being kept alive as long as ID and val are kept alive. And when they all go out of scope together, that's when the struct will be destructed.
Oh, okay, but you don't need it or have any way of referencing it. Right?
Correct. You have no way of referencing it. The presumption is here that all you really need from it are the individual member variables.
Okay. Thanks.
Sure. Any other questions?
No.
All right, let's go on then. So inline variables. So what does it do? You just use the word inline and you can define variables in header files, not declare variables, define variables. So for example, in foo.h, you could inline foo, which would be a global foo object. Okay, but why would I want to use that? Well, first of all, maybe you're making a class contained entirely in a header file. And maybe you want a single global object in your program, and the header might be included in many CPP files. Before, you had to ensure that one and only one CPP file contained the definition of the object, and now you don't need to put it in any of them. You can just use header files. So there's a couple of interesting notes on this one. Since constexpr implies inline, you can use constexpr to get the same effect. And if you use inline with thread local, then you get a thread local version or thread local copies of the variable. So you get one copy of the variable per thread. So if you need like a thread local variable for all of your threads, you can now define that using inline in a header file. So any questions on this? All right, let's move on. Aggregate extensions. What was an aggregate again? So for those of you who might have watched my talk on aggregate either 3 years ago or 6 years ago and are scratching your heads trying to remember, an aggregate is things we put inside curly braces for initializing stuff. So the part in purple here. So if we're initializing foo, which is a variable of the class myData, which is going to get a string and an integer, the aggregate is the part where we're putting the constants in here. So aggregate extensions, we've added a few new extensions to what aggregates can do now with C++ 17. So first of all, aggregates can have base classes now, and you can use an aggregate to initialize the base class and the derived class at the same time. And when you do that, you can skip the inner curly braces. So let's see an example. So here's an example. We've got a base class named data and a derived class named more data. So you could initialize data, as you see over on the left the left lower side, as taking foo and 1.4, and that would initialize an object of class data. If you want to initialize an object of class more data, then you can pass in, as you see in example more data y, test1 and 1.8 to initialize the base object, and then false to initialize the variables that are specific to data only. But as I said before, you don't actually need the inner set of curly braces. So if you do what's at the bottom example for more data z with test2, 5.4, and true, then that will initialize both the base class and the derived class at the same time. Any questions? All right, let's move on. So when would you use it? So this might be good if you want to initialize a derived class with an aggregate. All right, our next talk will be about mandatory copy elision. So what is copy elision? So you may remember that some time ago, maybe 2016, I actually made a presentation for the C++ users group on copy elision. But what it basically means is there are some times when you're going to be returning a value that instead of returning the value, copying it into a temporary, and then copying it from there into its final destination, what you can do is just construct it in the final destination. So the compilers are authorized to do this optimization for you, but not actually required to do the optimization for you. What's going to happen with mandatory copy elision is now, under some cases, the compilers will be required to do it for you, which will save you a little bit of work. Let's see how that works out. So since it was optional before, we always had to write a copy constructor and a move operator for the class, just in case it didn't use copy elision. So now we can skip that, but only for unmaterialized objects. Okay, well, what does unmaterialized objects mean? So an object is materialized if you've already created an instance of it. So here's an example of where you can use it. So we've got a class, myClass, and then we've got an argument foo, which takes parameters of variable myClass, and we've got a function bar, which is going to return a new myClass. So if you look down in function main, when you call foo my class, the my class is being generated, and before mandatory copy elision, we would create a temporary for my class, pass it into foo, which would get copied into foo's parameter struct. Now, the return value of my class gets copied directly into the parameter struct that the function foo uses for one of its arguments. Similarly, bar before would return a temporary, and then that temporary would get assigned to X with a copy. Now there's no need for the copy or the temporary. We can just have bar construct its value right in the variable X. And then if you look just a little bit further down, if you call foo of bar, the bar will once again create a my class, but instead of it being put in a temporary, it'll end up being constructed right in the arguments list for foo. Any questions?
I'm a little bit confused about what your
Sure.
comment that you used to have to create a copy constructor and now you don't. How does it do it without a copy constructor?
Okay, we're just about to get there in a minute, so hang tight and go ahead and ask the question again if you have 2 slides from now you still have the question. So first, when should you use mandatory copy elision? It'll guarantee better perf by avoiding copies, and as I said, it'll let us get away without writing copy constructor move operator sometimes. Now, what does that sometimes mean? So if you have already declared an object or already constructed an object, then you can't return that one in place. So you can't elide the copy. So if that's the case, and that's what this code here is doing, we're creating a obj object and then returning that instead of creating it in the return statement. That's when you won't be able to elide the copy elision. So basically what happens in this case is, since it's constructing it directly into the place it's finally going to live, which is outside the function foo when it first builds it, there's no copy required, it's just doing construction automatically. But if it is unable to do that for some reason, and this might be a valid reason that it couldn't do that because you've already declared the object, then you'd need a copy constructor and a move operator to be able to put it into its final place. So does that answer your question?
Yeah, it does. Thanks.
Okay, cool. Any other questions?
No.
All right, let's move on. Lambda extensions. So we've talked about lambdas before. Lambdas are nothing new to C++. We've had them for a while now, but they've added a few more extensions so you can do a few more things with them. So there's just been a small number of improvement. First of all, if they can safely be made constexpr, you can use them as constexpr at compile time. And then second extension is you can now capture this pointer, star this, to get a copy of the current object. In case the lambda lives longer than the calling scope, the lambda can keep the current object alive. And you can now capture objects by const reference. So let's take a look at what some of that might look like. So here is an example of one of the lambda extensions. So this is an example of a lambda, although in this case we're assigning the lambda to a name. And because it is something that can be made const, it can be called at compile time and used when you're doing some template metaprogramming. So for example, the standard array int squared 5 can be called at compile time, and the 5 will square to 25. So when your code is finally written, that'll be written as int, comma 25. So the second example, this is an example of capturing the this pointer. So in case L1 lives longer than the foo scope, the this pointer will keep foo alive long enough for it to be useful when L1 is finally called. So when might you use these Lambda extensions? It could be helpful in moving more code to compile time to speed up your app. Now, I think I've said this about Lambdas before, but whenever Lambda gets too complicated, I start thinking, maybe a regular function might be better. If you have to reason about it, if you have to think hard about it, then it really helps if the function has an actual name. So I personally would avoid functions where I capture a copy of the object because it becomes harder to reason about the lifetime of the object and what scope it's actually alive during. although I admit there could be some edge cases where it helps. So any questions about Lambda extensions? All right, let's move on. We've got some new attributes we can use. Just a moment. So 3 new attributes have been added by C++ 17. First, there is the no discard attribute. Second, the maybe unused attribute. And third is the fall through attribute. So sometimes you know that the value of a function needs to be referenced, or bad things are going to happen. Maybe you could return a horrible error that's got to be dealt with, or maybe you're returning some memory that you've allocated. If the return value is just thrown on the floor and not used, then you know there's going to be some problems with the correctness of the program. And that's when you'd want to use the no discard attribute. On the other hand, sometimes you know that this thing I'm passing in only gets used in rare cases, like when I'm debugging, in which case that's when you maybe want the maybe unused. And fall through is good for documenting intentional fall through cases in switch statements. So let's see some examples. So let's say you've got a function foo that's returning an int star. That means you've probably allocated an int on the stack and you want to make sure that it doesn't get discarded. Let's say you've got a function bar that takes 2 parameters, and the second one is only rarely used in case you are debugging and have some special debug flags set. And here's an example of fall through. So maybe if you are trying to load a web page and you get a 404 error, you want to print page not found before you print bad request, and you want to return request error for both of them. Now, generally, I've heard programming advice that case statements with fall through is bad programming practice, which is why a lot of compilers will emit warnings when they see it. This is a way to tell the compiler, yes, I'm doing this intentionally, there's no need for a warning, but you might also consider fixing your code if that happens, because it might be better to just not have the fall through. When to use new attributes? I'd say sparingly. Every one of these, in my opinion, makes a suboptimal design choice, so maybe consider refactoring your code first. And they might be useful for adding to old code as you're increasing the warning level. So if you've inherited a very old project, you're trying to bring it up to modern standards, and you're getting warnings all over the place, and it will take you forever to fix all these warnings, that might be a perfect time to use some of these. Any questions? All right, let's move on. Nested namespaces. So I don't know if you can tell that's a Russian stacking doll, but it's an owl instead of a doll. So the fun thing is, of course, owls build nests, and these are nested. Anyway, enough of that. So what does this do? It allows an easier way to specify a nested namespace. So before, if you wanted to specify a namespace inside another namespace, you go namespace A, open curly brace, namespace B, open curly brace, put your stuff, close curly brace, close curly brace. Now, if you just want to talk about a namespace A, which has a B inside it, which has a C inside it, you can just reference it very quickly and easily by A::B::C. So when would you use this? I'd say this is good. Go ahead and use away all you want to. Defined expression evaluation order. So what does this mean? So a lot of times when we look at our C++ code, we make implicit assumptions about the order these expressions are going to be evaluated in. Yep, this one first, then this one, then this one. That's the way I would read that. But it turns out that some of those things that we were thinking about, the compiler wasn't actually required to do, and the compiler might have done in a different order. So now, for all these cases below, I'll give you a minute to read them in just a sec, the compiler is supposed to do expression 1 first, and then expression 2, so that you can understand what order they're being evaluated in. Okay, any questions on that? All right, let's hear an interesting example. So Josuttis had an interesting example in his book where you've got a standard string and you're going to do some replace operations. So what if the replace operations don't happen in quite the order you expected? As a programmer, you'd probably expect the first one to happen, and then the one that's logically further to the right to happen, then the one that's logically further to the right to happen. But it wasn't actually required until now that the compiler do it that way. So you might expect it sometimes works if I believe after you make these substitutions. But in practice, before C++17, you could get any one of these. It sometimes works, I don't believe, it even works some till don't believe. Well, you get the idea. If they operate in a different order than you expect, then the results will be very different than you expect. And fortunately, we can say goodbye to that now. So when to use it? Well, this is one of those things that we are going to be using whether we like it or not. But overall, I think it's really good. It'll be one less thing for the programmer to worry about. At least it will be defined, so it will be the same all the time and the same in all compilers. Note this doesn't handle every single case. So the line below, I equals I plus 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 I, the operation order is still not defined, but we really shouldn't do this. Any questions? All right, relaxed enum init from int. So before, if you wanted to initialize an enum, you had to use an enum variable. Now you can sometimes initialize the enum using the underlying int. So let's say you have an enum class weekday, Monday, Tuesday, Wednesday, etc., etc. You can now, using the aggregate extension in the curly braces, initialize it with an integer. So the first line, day 1 of curly bracket 0, is now okay with C++17. However, you still can't assign them. This is just initialization, not assignment, that has now been allowed by C++17. So when would you use it? So I'm not sure I would use it this way, but you could define a new enum type based on the underlying init type, underlying integral type, without having to specify all the values. So we could have an enum myInt, which is a type character, and you might want to specify all 256 of the values that it could be, or you would normally have had to do that just to declare one int of value 42. Now you can just declare one int that belongs to that enum and give it a value right away. Again, I don't see any obvious use case for that. So any questions on this feature? All right. Fixed direct list init with auto. That's a bunch of words. What do they all mean? Let's put them together and get down to what it does. So before, if we were using an initializer list to initialize something, there's some cases that worked when they shouldn't, and some cases that didn't work when they should. So the first case, int x of 42, that works just great. It does exactly what we expect. X now has a value 42. The next line, auto a42, you would expect it to create an integer with value 42. It doesn't, it's an error because auto doesn't know what kind it should be in versions of C++ prior to 17. And then the next line, it works when you'd think it shouldn't. So you would think auto should have no idea what the type of B should be, but it decided that B, of course, must be a standard initializer because that's what you wanted, right? When that maybe wasn't exactly what you wanted. So now that they've made these changes, the auto A42 will create you an int of type 42, just as you would expect. And the second case, which you would have expected to be an error, is now an error. So when would you use this? Now note, strangely enough, this is actually a breaking change. C++ does make breaking changes from time to time because there's one old case which is now an error, although I'm perfectly happy that it's an error. And I would not go out of my way to use this, so at least not as shown in the example. While auto is good, I generally prefer the actual type if I didn't need the auto for some reason, but I could agree that it might be helpful in some kind of template programming where you don't know what type is coming in. Any questions? Okay, now here's a fun one, hexadecimal floating point literals, for when you really, really, really want to be very exact about what your floating point number is. So what it does is you can now specify floating point literals in hex to get an exact representation. So here's an example of us doing that. The purple code is a floating point literal in hex. Now these things are kind of hard to read. I get the 0x1, but what is this P4 thing? And I see the 0xc, but then .68. That's kind of confusing. Let's take it apart and see what it actually works. So the mantissa is written in hexadecimal, and the exponent, everything after the P, is base 2. So for instance, 0xcp2, the mantissa is C, which is 48, or I'm sorry, which is 12, of course, in decimal. And the exponent is base 2, so it says P2, that's 2 to the second because of the 2 after the P. So 0xcp2 is actually 48, or 12, which is the C, times 2 to the second, which is the P2. And again, when to use this? When you really, really want an exact value. Any questions? All right, this is an easy, oh, Robert, I see you have your hand up. Go ahead.
I meant to turn the mic on. So does the math work?
I presume that it does. Do you mean, is my example correct?
No, I just mean you have these exact things and then you start using them in math. I mean, what's the difference between doing it that way and using a floating point?
Okay, so yeah, with floating point, your math is very rarely exact. So if you have a bunch of exact values and you do certain operations that don't involve division, you will often get precise values when you're done. Now, once you start dividing, things are all over the place. Once you start doing a mod, things become a little bit less exact. But as long as you stick to a very narrow sandbox, you can make some exact math. Does that answer your question?
Yeah, I guess so. Thanks.
Okay, UTF character literals. This one's a pretty easy one, actually. So before, you could use the U8 prefix for strings to get UTF-8, but it turns out you couldn't use it for characters. That was just a little bit of an oversight. So now with C++17, you can use it for characters too. So here's an example how to use it. You just say CH equals U8, and then in single quotes, 8. And you now have UTF-8 character with a value 8. So when would you use this? Whenever you need a single UTF-8 character. All right, so those were the big features. Now, all of them seem reasonably small compared to the sum of the features that we got in C++11 and C++14, which really changed the way we work. Most of the features we've seen so far have been of the nature of rounding things out, fixing cases that were slightly wonky, adding a little bit of extra functionality. And some of the small features are no different, but let's move into them. Exception specifications as type. So we've probably already thought that the exception specification, such as no except or not having any exception specification, should have been part of the type of the function. And maybe with some compilers they were, but it wasn't actually officially part of the spec. Now it is officially part of the spec. So for example, no except is now officially a part of its type. So let's look at when you might want to use it. So you might want a function pointer of a type guaranteed not to throw, and you want an error if you try to assign some throwing function to it. So that's the first example here, whereas we'd have void a function pointer with no exception, so guaranteed not to throw. And if we assign some function that won't throw to it, the assignment will work. And if we assign some function that might throw to it, we'd expect to get an error. So any questions on this? Okay, static assert. So in the past, with static assert, the first argument was always a quoted string message. And now, I'm sorry, the second argument was always a quoted string message. And now you can do the static assert without the message. Here's a couple of examples. So before, you had one with the message. Now you have one without the message. In C++17, both are fine. Personally, I think asserts are better with a message, the more information you can give when an assert happens, the better off whoever has to read the assert will be. But there could be some cases where you might want to not have it. Okay, we have a new preprocessor, has include. So in the preprocessor, this is going to check to see if a header can be included before you actually try to include it. So the example here is you could say #if has include, and let's say file system is the name of your header. Then you include the file system. Otherwise, you have an endif. Okay, seems useful. Why would we use it? How would we use it? What would we use it for? So you might want to switch which header you're including depending on what's available. And generally imagine this to be the case when you're compiling for multiple platforms. You might want one kind of header for a Mac, a different kind of header for Windows, a different kind of header for Linux, and yet another kind of header for Android, and yet another one for iOS. Now, a note here is that it doesn't actually guarantee that there's anything in the file. So that's up to you as a programmer to determine, but it does guarantee the file is there. And last note, this is a preprocessor macro only. You can't use it in the code itself. It's just something as part of the preprocessor, which is sort of strange they're adding new things to the preprocessor, because I think that C++ has been trying to move away from the preprocessor more and more, trying to provide templates and functions instead of macros, trying to provide constants so we don't have to use #define nearly as often. Although I guess we haven't really moved away from #include. All right, now let's talk about.
Quick question
yes.
about that. Does that work only for like library headers, or does that work for any header file in your file system?
It should work for any header file, because file system was a good example of a place, because different platforms will have different file systems. I used it for the example, but you could do it for anything.
Cool, thanks.
Welcome. Any other questions? Okay, now we'll talk about some template features. We're making a few additions to templates. So what you're looking at here, this is the carbon fiber base plate of a drone being constructed. That's sort of like the template upon which the drone is built. And this is for a racing drone. So first, class template argument deduction. So now, if there's enough information, which is most of the time, we can actually deduce template arguments instead of having to specify them. So when you look at the example labeled from, we had to specify the argument double in angle brackets, even though it was pretty obvious from looking at the values 3.14 and 2.72 that we were talking about some floating point or double values. So now you can create a standard complex without having to specify the double, for instance. So when would you use it? My advice would be to use this when the class type that's actually being used is obvious to any maintenance programmer. A few more details. So it works for copying. You can make a wrapper class that deduces. And you can replace the make pair, which I've seen a lot of in my code, with just a constructor with curly braces using aggregate. And sometimes the compiler is going to guess wrong. You can actually provide a deduction guide. So in the book, C++ 17, the complete guide, they talk about how to provide deduction guides. That's going to be out of scope for the overview of the language that I'm giving this evening. Okay, a compile time if statement. So the most important thing to say about the compile time if, and it's a shame he's not here to hear it, is thanks, Walter, because this feature came to C++ from D. It was Walter's brainchild, and it was D that was first to implement it. And C++ looked at it and said, hey, we want that. So as it says, it's going to calculate an if, then, else at compile time. So here's an example from the book. So template type name T, standard as string. So what it's going to do is it's going to try and convert the T that's passed in into a string. So you'll know at compile time what the type T is, but of course the template author doesn't know what type his template is going to be instantiated with. So if the type is the same as a standard string, then we can just return the string itself. If it's an arithmetic, we can return a call to standard toString. Otherwise, we can return a standard string of X, hoping that X is some kind of character array that can be converted into a standard string. And now we can do that at compile time, so we can use it in templates. So when would you use this? So it allow us to write templates that would otherwise never have compiled, like the example I gave you. It's also good for perfect forwarding. So if you don't know what perfect forwarding is, sometimes you've got a template that's given a reference. Sometimes it's given an R value reference. Sometimes it's given a value. Perfect forwarding means that if you give it a reference, what comes out of it is also going to be a reference. If you give it an R value reference, what comes out of it is also going to be an R value reference. If you give it a value, what comes out of it's going to be a value. If you give it a pointer, what comes out of it's going to be a pointer. Same thing with const. If you give it a const reference, you'll get a const reference out. So this is important because a lot of time you want the template to take whatever type comes into it and give you the exact same type back out. So that's what we call perfect forwarding. Let's see, this is helpful for tag dispatching. So if you have one variable or a tag that says what type something is, and then the other thing that is a thing of that type, you can take a look at the various types that it might be and call the right function for that type. And it can be used outside templates to help reduce the code size. So any questions here? Oh, one thing I thought I should explain, the difference between a reference and an R value reference. So you may remember the difference between L values and R values. An L value is something that has a name, something you can assign to. An R value is something that doesn't have a name. It doesn't have a designated storage location in the program. So R values are great for moving. And generally, when you want to move things, you want to move things with R values, whereas L values you generally want to assign to. There are a few gotchas with compile time ifs. So the unused branches, the ones you don't end up actually using, still have to be syntactically correct because the compiler has to look at all the branches to know for sure what the return type is going to be. And the return type could be affected by the else, even if it's the then that returns. One other thing to be aware of is normal ifs do short circuit compilation. So if you have if A and B, and A is false, then you'll never evaluate B. That doesn't actually happen with a compile time if. It's got to evaluate both. Okay, let's talk about fold expressions. So I first encountered fold expressions when I was reading a book on Haskell. Bartosz had some great things to say about Haskell, so I thought I would pick up the book and try to learn it and try to wrap my head around it. And this is about where it started getting interesting with all the fold expressions. But the general idea is, let's say you've got a big list with a bunch of arguments and you want to march through the list doing something with each argument. And maybe you want to march through it from the left-hand side or from the beginning. Maybe you want to march through it from the right-hand side or from the end. So this will allow you to add a binary or you apply a unary or binary operator to all the arguments. So an example of how this works is you might have a template and notice the type name ... So the ... is going to mean that you've got some unknown number of things of type T. And we'll have add all, which takes a pack of an unknown number of things of type T. And then what it will return, and an args variable, which is the one variable type T, and it will return ... plus args. So the ... plus is going to turn into a fold expression, which is going to tell it how to compact all the things and how to do the addition. So to look for an example of that, if you have ... and then the operator and then the args, you'll have what we call a left fold. And a left fold is usually what the programmer intends. And you can have that either unary or binary. You can have a left fold or a right fold. So for instance, for a binary left fold, you have a value, an operator, the ... another operator, and args. And the way that that will get put together with a left fold, you start from the left, so it'll be arg1 up, arg2 will be done, and then that'll be applied the operator to arg3, and then when that's done, that'll be applied the operator to arg4, and it will go on the list until it reaches the end of the list. So thinking about programming this way, certainly has changed how I have thought about the code. And I had to work really hard to wrap my head around this at first. But once you've wrapped your head around it, fold expressions can be a really powerful way. Programmers like it. So when would you use this? So before this feature, you would have to write a recursive template to do this, which stresses out both the compiler and the programmer who's trying to both write it and understand it later. So now it should be a lot easier on both the compiler and the programmer. So any questions on fold expressions? Okay, string literals for template parameters. So what does it do? It used to be you need to have external linkage or internal linkage if you wanted to pass a string into a template parameter. Now you can do it with no linkage. Sorry, what does that mean again? What's external linkage? What's no linkage? Let's do a quick digression into that. So string linkage types. So if you have an extern const char, that's something that has external linkage. It'll be available outside the translation unit or the file you're compiling. If you have const char hello 11, as we have here, that'll be internal linkage because it'll be internal to the file or the compilation unit you're compiling. But let's say you have some function and you just declare some static variable in the function. It turns out that actually has no linkage. And before this new change to C++17, you couldn't pass that thing with no linkage into a template. So now, with the goodness that C++17 brings to us, you can have some template greeting, and you can pass it some string that you have built with no linkage, like hello17 was the one from the function in the last slide that had no linkage. And now that will work. There's some things you can't do still, so you still can't pass just a bare string in. But you could pass in something with no linkage as we saw before. So if you declare this into a proper variable and make it static and put it in a function, you can still use it in template parameter. Any questions? So when would you use this? Before this, you could have a template that takes a pointer for an argument, but you couldn't really have a compile time function that returned the address of something, and this feature fixes that hole. Okay, placeholder types as template parameters. What does it do? You can now use auto to declare a non-type template parameter, and by non-type I mean value. So let's look at an example. So you might have a template, auto t class foo, and now you can declare foo of 42, and the auto will understand that 42 is meant to be an int, instead of you having to specify a variable as t that was an integer. Likewise, you could do the same thing if you wanted to pass in a single character. So when would you use this? Well, one example is you might have a string that sometimes takes you might have a template that sometimes takes a string and sometimes takes a character. You might want to define some compile time constants. Or you might be using auto as a variable template param. So basically you're using auto as the parameter for the template because the template doesn't know what type is going to be passed into it. And then you could pass in a value instead of passing in a type. Any questions? Okay, extended using declarations. What does it do? You can now use a comma-separated list of names in a using declaration. So for instance, look at the purple code here. Before you might have to say using base A is its own statement, using base B is its own statement, using base C is its own statement. You can just add them all into one line. In this case, it's nice because you're going to be using all the members of a derived class. You can just declare them once instead of having to declare them one line per. When would you use this? Maybe it would be good with variadic parameter packs or inheriting constructors. I don't see most code as really wanting to use this. I saw a lot of examples in the book, and most of the examples had added complexity for only a small benefit. So I don't actually recommend this, but there may be some corner cases in which they're useful. And starting with the template drone, I've shown you over the last several slides, putting together the drone bit by bit. And this is what it looks like when it's finally completed. So a template instantiation, if you will. So that was the first half of C++ 17, the new language features. The next half is the new library components, which I will be giving a talk on next April, because we've already done 92 slides, and I don't think we have enough time tonight to finish it tonight, and it might also have something to do with the fact that I haven't finished writing the slides for the new library components yet. Just possible. So here's some links for you all. Again, as I mentioned before, Lloyd will send out these slides and make the slides available on the website. So the first one is a link to the book that I told you about, Josuttis' C++ 17, The Complete Guide. The second one is a link to a Wikipedia article that also talks about what's new in C++ 17. Anthony Caldera maintains a website where he's been going through all the new C++ versions and talking about what's new in them. And if I'm giving this talk later at Google, there's an internal reference at Google that you can use. And that is the end of the talk. Thank you for listening. Are there any more questions?
Going once, going twice, going 3 times. Got them all during the talk. Not bad.
Well, thanks, everybody. I hope it was useful for you. I hope you learned something. If you want to see more of these, let me know, because they do take a lot of work. I can get started on reading the C++ 20 book so that 3 years from now, I'll have another talk ready for you.
They're great. In fact, for each one of those remedial classes that were new to me, and I went and wrote some software trying to do each one of those features.
Awesome. I'm happy to hear that they're useful.
Yep.
Thanks.
Yeah, no, I find these wonderful for quick reviews. Okay, folks, I guess with that, we will call it a wrap. We will see you next month. We're going to try something a little different next month, too. It's going to be a open debate. So we will see how that goes. Topic to follow. All right. Have a good one, and thanks again, Peter.
Welcome. Good night.